Yes, we can go over homework. So,
I didn't do it.
you didn't do homework? So you don't have a question about homework?
No.
You just want to go over all the homework problems?
I want to know what the homework looks like.
This is my home. Your home is somewhere else. That's where you're supposed to do that work. Huh?
Literally, I have completely forgotten to do it. On Monday, I was planning on doing it Monday.
It's not that bad.
I believe it.
Exercise 1 introduces you into another type of logic.
Exercise 1 was weird.
Oh, Leah did it.
I did
Weird.
what I could.
So what couldn't you do? Let's start with that.
I couldn't do number 1.
You couldn't do number 1.
Yeah, I didn't know what to do.
What
I was
part?
confused.
So it asks you, so it doesn't ask you to really do anything yet.
That whole thing is like an example or something, and then A and B are what you're supposed to do.
Right, so let's look at A and B. So it says, give examples and analysis to show that the following are not truth functional connectives. Okay,
I didn't know how to do that.
so Mr. Smith believes that. We're saying this isn't a truth functional connective.
Yeah.
Maybe let's do a quick review of last time and then get back into that.
Okay.
So remember that we talked about atomic sentences, which is like getting to the gist of what something's saying, or the minimum sentence you can get out of something.
Okay.
And then we talked about different sentential connections that you could put on that, like and, not, or. So an atomic sentence would be the sky's blue. Another atomic sentence would be James is green. So I could say the sky is blue and James is green, and is operating as a sentential connective, right? I could say not James is green, or James is not green. So I'm applying the sentential connective not. So you have James is green. I'm going to apply the sentential connective not, and that's going to give us James is not green, or it is not the case that James is green, is the way the author suggested thinking about it, right? And the rest of these kind of make sense. The sky is blue or James is green. If the sky is blue, then James is green. The sky is blue if and only if James is green. So these were different sentential connectives. On top of that, they were truth functional sentential connectives. And what did we mean by that truth functional bit?
They're dependent on.
They're only dependent on whether or not its component sentences are true or false.
Right.
So if I wanted to know, is it the case that the sky is blue and James is green, how do I determine that? I check to see if the sky is blue, and I check to see if James is green. If both those things are true, then the entire sentence, the sky is blue and James is green, is true. Otherwise, that sentence is false.
Right.
Does that make sense?
So you can get a truth value out of it.
So you can determine whether or not it's true or false just by knowing if the atomic sentence we were working with is true or false. So looking at not. So we say the sky is blue. Is that true or false?
True.
It's true. So that means that the statement the sky is not blue is false.
Right.
We know that the statement the sky is not blue is false because we know the statement the sky is blue is true.
Right.
Now look at this. Mr. Smith believes that the sky is blue. True or false?
There's no way.
Can't say.
You can't answer the question. You don't know what Mr. Smith believes.
So
If it's true, he could believe that. If it's false, he could believe it
Is
too.
that a statement then?
it's not
So-
truth functional connective.
How would
So
you like
the sentential connective, Mr. Smith believes that, is not a truth functional sentential connective.
Okay.
So if I add on Mr. Smith believes that, if you think about the word sentential connective real quick, what does that mean? It means something you can connect onto a sentence. So these are things that we can connect onto sentences. Can I determine if the resulting sentence that I get when I add on Mr. Smith believes that, if I add that onto a sentence that I know is true, can I still determine whether or not the sentence is true or false? Or if I add that onto a sentence that I know is false, can I still determine whether or not the sentence is true or false? If I can, it's truth functional. If I can't, it's not truth functional. And obviously with logic, we only care about truth functional connectives. We couldn't care less about what Mr. Smith believes we care very much about not,
Right.
right?
So literally in A and B, you just have to put some
So you
atomic sentence at the end of that.
and say that it could go either way if
Wow.
it was true or
Right,
false.
you can't, so
Can't determine
another
it.
way to think about it is, do you know how to make it, can you make a truth table for it?
No.
If you can't make
I
a
didn't
truth
know
table
how
for
to.
it, then
You can start.
it's not truth functional.
Right.
You'll always be able to make a truth table for a truth functional connective.
What does it mean when it says and an analysis?
And an analysis, it means,
Is that a true function? Is that a
yeah,
table?
explaining that it's not a
It's
truth
just
functional
an
connective.
explanation.
Oh, it's just a sentence.
Yeah, it's,
Yeah.
I mean,
I thought analyses were like, okay, pull up your truth tables.
you could do what they did.
I think that's why they gave you the
If it's
example,
true,
follow it that way.
then the fact that Mr. Smith believes it could be true. It could also be false. It's possible that's true. And then, same thing with, it is necessary that.
It is necessary that the sky is in blue.
True or false?
It's not necessary.
Yeah. True. That makes sense that it's not a true sentence.
Seems like true. True.
Alright, so that was number one. So does number one now make sense what you were trying to do? Alright,
Was there another
I
word?
would
No.
basically do a lot of them.
What's that right there?
it's all a workup to number one. So they're doing a whole elaboration here that it is possible that is not a truth functional connective.
It is possible that 2 + 2 = 5, and that's not possible.
Because it's possible.
Right, so look at
They use the diamond to say.
it is possible that 2 + 2 = 5. No, that's always false. It is possible that there is not any life on Mars. Yeah, that's possible. It's possible that there is life on Mars. It's possible that there isn't life on Mars. So here's
it's
possible that there is life on Mars. Here's possible that there isn't life on Mars.
true.
So with one sentence, our truth table looks like this. With another sentence, our truth table looks like this. So our truth table is dependent on the actual sentence, not on the truth or falsity of the sentence.
Yeah. That's what was throwing me off when I
So
went
they
from A
intentionally
to B.
gave you a harder one. It is possible that is a harder sentential connective to analyze than Mr. Smith believes that.
Right, I was trying to do what they were doing and get sentences that did that, and I just couldn't come up with any, so I was like, I don't know how to do
I don't know if you could attach an atomic sentence on the end of either of those and make it work like it is possible that 2 + 2 is 5.
And make it work, it is possible that the Patriots win the Super Bowl.
No, what I'm saying is, in number 3, then diamond W was only false.
Right, it is not possible for 2 + 2 to = 5. So remember in mathematics, one of the early conversations we have in our math classes, we say that there's a difference between, one of the fundamental differences between math and science is that science says something's true if they've never seen it false.
Right.
Math says something's true when it's impossible for it to be false.
Right.
So it is impossible for 2 + 2 to = 5.
Why is that impossible? Well, you have the set containing the empty set containing the empty set, comma.
Well, it's a definition thing. 2 + 2 is 4. 4 is not equal to 5. If you allow 4 to equal 5, I can prove any declarative statement you want. One of the typical examples when the guy said it is, so the numbers he said is, if you allow 0 to equal 1, I can prove anything you want. And the guy challenges him and he says, okay, prove I'm the Pope. And he says, okay, since 0 is equal to 1, add 1 to both sides, you have 1 is equal to 2. You and the Pope are 2, therefore you and the Pope are 1. Therefore you're the Pope.
That was a fun.
Like
No.
such.
To say you two are 1 is to say you are identity. It's the identity element. It literally means you two are the same. There's nothing wrong with that. The proof is perfectly valid, the premise
Okay,
you
say
can't
that.
operate on. That's why if you allow one contradiction to mathematics, the whole thing falls apart and you can prove anything. If you allow 0 to equal 1, then 1 equals 2, right?
Mm-hmm.
You and the Pope are 2. Therefore, you and the Pope are 1. Therefore, you are the Pope. Make sense?
Yeah, but you and the Pope are 2 doesn't mean that you and the Pope are 1 because you can also be 1.
2 is 1.
Yeah. Because he added 1 to both sides.
If
'cause
0 is equal to 1, then 1 is equal to 2.
Yeah.
So,
Oh,
you and Pope
Right,
are
I'm not
2,
seeing
Right,
that.
right.
and then so you're 1,
You add
So you're the
0
same.
to both sides.
You add 1
you add 1 to both sides.
Oh, because 0 is 1.
No. If 0 equals 1, add 1 to both sides. What is 0 plus 1?
1.
1. What's 1 plus 1?
2.
2. So I just added 1 to both sides. Well, I did one side, I did to the other.
Oh, 0 plus 1.
Equals added to equals are equal, right?
0 plus 1 should equal 2.
It does!
What?
0 plus 1 is equal to 2.
No!
Why
There
is
should be
0
a 2
plus
on
1
the
equal
left hand
2?
side.
So
Because if 0 equals 1, then 1 plus 0 equals 2.
Right, I can make anything you want. I could also make 0 equal 2. That works. So if 0 equals 1, then 0 plus 1 is equal to 1 plus 1 is also equal to 0 plus 0. 0 equals 2.
Oh.
I can prove anything if you allow 0 to equal 1.
Okay.
So when we say something is false in math, we mean
That's
it's
it.
impossible for it to be true.
Nah, good boss.
And that's not even the same thing as a 0 probability. We mean impossible. Not 0% chance. We mean impossible. It can't happen. Okay. So that was number 1. Any other questions? Any other homework that people who actually looked at the homework got stuck on?
I
No,
basically
which
just
problem
didn't
did you
do
get
the
stuck on?
last few. Just because it was.
Just because it got repetitive? Or why?
I didn't really know how to do some of them.
Name one that you didn't know how to do.
I didn't know how to do
15.
Yeah, see, there's tons. Well, there's.
No, it's
not
Don't
tons.
act like you know.
15. Actually wasn't that hard. I just had to
So, if P and Q are distinct atomic sentences, so they're not the same, the sentential connective P and Q tautologically implies which of the following?
I don't know what you did there.
15.
He said sentential connective.
I don't know what I said wrong.
15.
The sentence P and Q tautologically implies the following. Oh, I thought that's what I said, so
No.
I don't know what I said wrong. Anyways, so all you got to do is figure out which of these it tautologically implies, right?
Well,
Now remember what
what is
tautologically implying?
A
Okay.
truth input.
What's a tautology?
No matter what you plug in, it's always true.
Yeah.
Yeah.
A tautology is an always true statement.
Yeah.
So tautologically implies just means it's an implication that's also a tautology. It's that simple.
Okay.
So we're looking
Stop
at
asking questions.
P and Q tautologically implies what? Well, it tautologically implies P or Q. I'm guessing that there's many that it implies. Because it's also going to do E also works. But we'll just do C.
Yeah, I don't know what you're
Yeah, I
saying.
think it's wanting multiple answers.
Yeah, there's got to be multiple. So we'll just do it. So we have P. So I'm looking at P, Q. My antecedent is P and Q. And I'm doing implies. Which one did we want to do?
15?
Yeah,
Oh, you
but
want to do
C works.
P or Q.
P or Q.
Yeah.
And then we're doing P and Q implies P or Q. Now a way to make this, and parentheses there in case.
There's not that.
What?
He's looking.
You
What
just
do
make
you-
a truth table.
What are you looking at on the last one?
This?
Yeah.
I am showing that P and Q tautologically implies P or Q.
Oh,
Okay, wait. Is
I
it-
am showing that this
Oh, yeah.
implication is a tautology.
okay. Okay.
Yeah. Gotcha.
I don't even.
Oh, because you're choosing or.
Yeah, I just picked, I know that there's multiple of them, but I just picked one. Now here's the way that you can make it make sense in your head, real quick. If I know that P and Q are both true, then do I know that P or Q are true?
Right.
Yeah.
Yeah, that's always true.
Right.
So that's intuition, if you just like say it out like that this is a tautology, obviously.
Right.
If I know P and Q are true, I for sure know P or Q are true.
But they're not always true.
That implies is what he's trying to figure out.
This implication is always true. So let's just do it. So we got true, true, false, false, true, false, true, false. So all the possible combinations. We can either have both P and Q are true statements, we can have P as a true statement and Q as a false statement. We can have P as a false statement and Q as a true statement, or we can have they're both false statements. So these are all the possibilities. And what we're saying is no matter what the values of P and Q are, this is always going to be true.
Right.
Okay, so if I know that P is true and Q is true, is P and Q true or false?
True.
True. Alright, if P is true, Q is false, P and Q is
False.
false. If P is false and Q is true, P and Q is
False.
and if they're both false, it's
False.
perfect. Now, or, remember what we mean by or, we mean the inclusive or.
Mm-hmm.
One and the other.
At least one is true, is what we mean
Right.
by that or. So if P is true and Q is true, P or Q is
True.
true. At least one of them was true, yes. If P is true and Q is true, at least one of them was true,
Yes.
yes.
Just have
If
false,
P's
but
true, Q's false.
Oh,
Yeah.
if P is false and Q is true,
True.
true. And if they're both false,
False.
false. Wonderful. Okay, and then implication was the weird one. If this is true, is this true?
Yes.
What the heck? That
Yes.
is weird.
Yeah, that is.
If this is true, is this true?
You mean if that's false, that's true.
No.
If that.
I said it right. If P and Q is true, is this true?
Yes.
P and Q is false.
It's true.
But if it's true, is this true?
Yeah.
Yeah. What? Vacuously true. Remember these are if-then statements.
Right.
If P and Q, which is a false statement, if P and Q, then P or Q. So it's vacuously true. Here's the example I always give. If Donnie's a purple dragon, then the sky's on fire. That's true. It's vacuously true. Is Donnie a purple dragon? No.
That's
So you
both-
can't check anything.
But isn't that both of them false statements?
Okay. If Donnie's a purple dragon, 2 + 2 is 4.
There you go. Because this guy on
Alright.
fire.
Yeah.
Vacuously true. Is it false? Remember, that's another way to think about it. If
Why did you
Donnie's a
say-
purple dragon, then 2 + 2 is 4. Is that false?
No.
Right, but why did you say?
If it's not false, what is it?
True.
Why were you
It's the
saying
definition of not false.
true implies false? What was saying? You were saying true implies true. We're dealing with false implies true.
Okay, so on this one, if this is true, is this true? If P and Q, so if false is true, is P or Q true?
What does that mean if?
Yeah.
Okay, sorry.
So confusing.
I'll just say it
It's
this way.
not
If false, then true is
True.
true. Okay. If false, then true is
True.
true. If false, then false is
True.
False.
true.
True. It's true that it's false.
It's just like.
If Donnie's a purple dragon, Jacob lives on Mars.
Right.
Yeah, you can't check it.
That's the truest
Is it
thing I've
false?
ever heard.
If it's not false, then it's true. That's what we mean by not. Not false is true, not true is false. Okay, so it's a tautology. Da, 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 da.
But again, we only care about
So
that
would
top
you
one.
do that for all of them to try to see which one it is? See which one's a false?
Once you get comfortable enough with them, it'll just be obvious to you which ones are and which ones aren't. That's what the author's trying to do by giving you so many.
Okay.
So, like, obviously,
Yeah,
We
that's
didn't
what.
have to do this, now that makes sense.
Right, that's what it felt like. with the
Okay,
others as well.
one more thing, I did one more step than the author's ever gonna do on proving something is a tautology.
You did the last one?
I did this last row. He never does, or this last column. He never does the last column. Says all you care about is every time you have a truth here, do you have a truth here?
Right.
Yeah. So if we have a truth here, do we have a truth here? Yes. If we have a truth here, do we have a truth here? Yes. If we have a truth here, do we have a truth here? Yes. If we have a truth here, do we have a truth here? Yes.
Okay.
Every time we have a truth here, we have a truth here. That's all we care about.
Oh, I
We
see.
don't care about when we have a false.
I see what you're saying
I
now.
don't see what you're saying.
Where do I have a truth in this column? When is my antecedent true? It's only true in this case.
Yes.
And my conclusion was true in that case. If that happens, if every time your antecedent is true, your conclusion is also true,
But
But it's not.
then it is. Every time this column's true, this column's true. Not every time this column's true, this column's true.
Right.
I'm still not seeing it.
Okay, just because it's false doesn't mean it's not true.
How can I make this make
No,
sense?
Okay, what I'm saying is
I'm
he
sorry,
says
guys.
every time, so pretty much, every time you see
Hold on, I got a sentence for you. Imagine I have a motion sensor on my door
there you go.
that turns on my lights every time I walk in. Okay? Then every time I walk in my house, my lights are on. That doesn't mean every time my lights are on, I'm walking in my house. It means every time I walk in my
That's not
house,
what the-
my lights are on. Every time we have a truth in this column, we also have a truth in this column.
But that's only the case at the very top.
Yeah, that's because that's the only place where we have a truth.
Oh,
Like very think simple.
and that makes it all true.
Donnie walked in the door, then the lights were on.
Donnie did not walk into the door.
Sometimes the lights are on. Michaela was in here. That didn't help like I thought it would.
It just doesn't make sense. 'Cause you
Look,
know it's only in
is
the
it
top.
not legitimate to say, for that and statement, every time it's true, then it's true.
Every time the antecedent is true, the left-hand side of our implication, which is this column, if every time the left-hand side is true, then the right-hand side is also true.
There's only one time it's true, but still with all the falses, you can still say every time it's true, it's true.
So if every time the left-hand thing is true, the
Okay.
right-hand thing is also true.
I agree.
Then it's a tautology.
I understand what a tautology is. I'm just not getting what you're saying with. You're pointing at a false.
Okay, imagine
You're
for a
saying
second.
This false is true.
Imagine for a second
Yeah.
we didn't know these values. Let's say it this way. Imagine I didn't know if those were true or false.
Okay.
I still know that this is a tautology.
Because
Because when it was true over here.
Only when you're dealing with implications.
That's what we're talking about.
Okay.
So I'm saying when the author is showing that something is a tautological implication,
Oh.
he's not going to write this column. He's just going to say, every time we have a truth here, do we have a truth over here? Yes. Because we don't care what these values are.
But
Fine.
False implies anything is true. Right?
Okay.
If Donnie's a purple dragon, then
Yes.
doesn't matter how you finish it, it's always true.
Okay, you just got me at, you pointed at a false and said, okay, this
I
is
think-
false, but it's really true,
Okay.
and it implies truth. So,
I don't think I said that, but
You
something I
pointed
said
at
was
it.
interpreted that way.
when you pointed at the false
Alright.
and you said, this is true.
Anyways, so now does it make sense?
Yeah.
Every time we have a truth value in this column, we have a truth value in this column. Therefore,
So
it's
it's
a tautological implication.
Okay.
Make sense?
Yeah.
Jim's over here.
Yeah, you're,
Yeah.
I don't know what to do for you if you miss the first class.
Two.
I'll have,
go read the
Oh,
book.
first rule.
I think I'm gonna go into busy tomorrow, so I think I'll have all the lectures uploaded by the end of the day.
Our internet's crap, so we can't upload it here.
Yeah, either that or I gotta go to the academy and break in and do it.
Should do it at our house.
Does that good internet?
Yeah.
You sure?
Yeah.
All I know
You
is
sure
that
it's good internet?
I know it's
Originally-
definitely better than the academy.
Oh no, no one's at the academy for saying. I can get 100 down.
I can get better ping at Dad's house than the academy.
Oh well, ping's not the same thing. that's like latency. So that has to do with the fact if you're playing League of Legends with someone on the opposite side of the world, the speed of light is still the speed of light. They do a move. There's some central computer trying to keep track of the state of both your positions. So their move has to be sent to that computer, your move has to be sent to that computer, and it has to resolve that. So if it takes 2 seconds to do that, that's a 2-second lag time. And the computer might have had to decide, actually, since this guy hit you, you're now over here instead of where you thought you were, and so you suddenly jump back.
Right.
That's why there's
So that's not the same
Why you
thing
lie in the game.
as
Well,
good internet
yeah,
speed.
and that's why there's
latency.
servers like NA servers.
So that's why you need close
Stream
server speed, not necessarily better internet. So that's a physical problem, and there's nothing you can do about that. The speed of light's the speed of light. We can't speed that up. Well,
Well,
we can to some extent.
Then how come my internet's worse some days
Then how
and
come,
better
so,
others?
yeah.
Say that again?
How come my internet's worse some days and better others?
Well, there's two things. There's, if you're talking about latency when you're playing a video game, that's one thing. That's not necessarily connected to your internet being bad. It could also be part of it. But even with perfect internet, you could still experience latency.
Right. Night Blue will get on the UK servers and then have terrible.
Right, that's a very stupid thing to do. If you're in America, don't be on UK servers. There's a reason that they set up the separate servers that they do.
Right.
It's user experience. Anyways. So that was homework. Any other questions on homework?
Yeah, I
That
don't
was
need that.
basically
I'm
what's
going to go
happening.
through and go.
Yeah, that's what all the girls say.
You
Hey.
want somebody else?
Nah.
By that definition, Leah is a boy.
No.
She didn't say it.
That she was gonna do it?
Oh, actually.
Alright. Now, so we're ready to move on?
Yes, sir.
Okay,
I don't know
so
what more there is to talk about. But yeah.
we finished chapter 1. We're obviously done.
I don't understand how you can get more in depth with this.
We haven't even done a proof yet.
Yeah, implications.
Oh, we dropped truth tables.
Yeah.
Alright.
You did an algebra proof.
So, those are basic sentential connectives. Now, so what did that enable us to do? That enabled us to, so we had atomic sentences that we could determine the truth or falsity of, and then we had truth functional sentential connectives that we could use to combine sentences to determine the truth or falsity of. Now we need a way to infer something else is true. We need to take our present information and come to some new conclusion. Inference. You all intuitively understand what it means to infer something.
But that's what
Yeah.
science does, not what math does.
No. No.
No, I don't understand inference. Explain it using math.
And inference isn't it?
Every proof you've ever done. If this is true, then this other thing now we discovered is also true. You proved that that's the case. You didn't know that was the case going in. You didn't sit down in geometry, me give you the axioms and say, therefore the Pythagorean theorem. You had to work up. You had to infer a lot of things, infer a lot of things, infer a lot of things. All your theorems build,
What do you
build,
mean
build,
by
build.
infer? Because
Proof is also true as proof is true as a logical implication of what we were given.
Right.
okay.
You need to demonstrate
We're
that that's the
thinking
fact.
We're thinking of Dad gets mad at you because you left the water on. Oh, I inferred James was going to turn off. You know what I'm saying? It's not a proof.
Okay,
Yeah.
so that's what chapter 2 is going to be the start of. Sentential theory of inference. How can you determine the truth or falsity of some new statements, some new sentences, based on the sentences that you have?
So,
So in short, what we're talking about doing is, we now want to come up with the rules for starting with axioms and building theorems. How can we go from just our axioms to building theorems now?
Right.
So we now know our axioms, we now know how to talk about our axioms, we now know how to identify if that axiom and that axiom are true. Now we need to talk about how we use our axioms to infer new things.
so when I say I inferred something, that means I proved it.
Well, the English language is the English language. And many words have different meanings. Like one of the things we went over last time was how only if
Oh yeah.
means one thing, and when we use it in this class, we mean another thing, a very specific thing by it. But sometimes used in this way. Well, I was talking about the word but as another one. So the English language is subtle. It's always changing. And what a word means, for the most part, is just how the most people are using it. I mean, what other metric do you put on it? But when we start to use it in a mathematical context, we nail down its definition, what we mean by it, and that's the only way that we use it. Like or is a good example. Okay. So that's what we're trying to do. We're trying to develop the rules that we would use to go from starting formulas or premises to some desired conclusion. And so we're going to be talking about those rules today. Now, whatever those rules are, whichever ones we decide to allow and not to allow, we have two criteria that we need met every time. So the two major criteria, the first one is, given a set of premises, the rules of logical derivation must permit us to infer only those conclusions which logically follow from the premises. So whatever these rules are, I don't want to be able to prove something is true that doesn't logically follow from my premises. Now you're reading that and you should probably be saying, logically follows? What? Isn't that what we're trying to define?
Well, logically, it just means it stacks.
So we're going to have to work out this logically follows. So I'm going to give you the two premises. If you're kind of scratching your head and just not quite sure what it means, let's just get intuition first. And then we'll narrow down as we go, because we need to have a lot of conversation about this logically follows.
Derivation? How do you say that?
Derivation.
Derivation, what does that mean?
A derivation, when you derive something from something else,
Okay.
you could look at a proof as a derivation.
Given a set of premises.
The rules of logical derivation, the rules of how you apply things to come to some conclusion, must permit us to infer only those conclusions which logically follow from the premises.
Okay.
In other words, I can't start with the axioms of Euclidean geometry and come up with hyperbolic geometry conclusions.
Right.
Right? Two different bills. So the first one makes sense? Alright, the second criterion is word for word the exact same as this, except for switch out only with all. So we want to only come up with those conclusions which logically follow from the premises, and we want to come up with all the conclusions. We want to be able to come up with all the conclusions.
We don't know.
We won't personally work through and prove every conclusion, but we want our rules, if we use them to infinity, to be able to derive every possible conclusion.
Right.
Make sense?
I don't understand why that was necessary to put all because.
The second?
Yeah.
So
is that one saying?
maybe we'll jump for a second to wrap our head around the second one. So I can come up with a rule of inference, which is just this. If P is true, then P is true. Okay? Notice that we don't have a problem here with the first rule. Does P logically follow from P? I know we haven't gone over logically follows yet, but if P's true, do I for sure know that P's true? Yes. Okay, here's your one and only rule. If P's true, then P's true. Well, thanks a lot. That doesn't really help me do anything. So the first criterion basically says you can't come up with a bunch of contradictions. The second one's saying, and you have to be able to come up with something useful.
Right. Right, that would make sense.
You can't come up with a bunch of contradictions, but you...
I can't have a set of premise that prove that James is green and James is blue.
Meaning,
Yeah.
it makes sense.
Or James is green and James is not green, if we're using a contradiction.
And purple.
Alright. So, I know that we don't have a deep understanding of what these mean yet, because we don't know exactly what logically follows means. But you have some intuition for what we're going for here. We don't want to be able to prove things that should be false. And we want to actually be able to prove something. Good? Okay. So the question that... Oh, go ahead.
What does it mean to logically follow?
So intuitively.
Yeah, so when you look at this, I mean, so you might have been thinking in your head, okay, now we're going to come up with what it means to logically prove something, right?
I was just thinking.
And now we're sitting here, well, this is what we want to do when we're logically proving something, just make sure it logically follows. You see, it could be some circular reasoning there, and we don't want to go in circles. So we need to be very careful about what exactly we mean by this logically follows. And that's what we're going to have discussion about the next little bit. So before we get into a definition of what it means to logically follow, let's just wrap our head around it intuitively. So we want to be able to say Q logically follows from P is true in every interpretation where P is true. In other words, every time P is true, if Q is also true, I want to be able to say Q logically follows from P.
Just like our table, just barely.
Yes. But he's using interpretation the way we did before when we were talking about tautologies. I don't know if we went into this that much, so let's get into what exactly he means by... I just wrote interpretation here. I was supposed to write sentential interpretation. So Q logically follows from P is true. It's true that Q logically follows from P if in every sentential interpretation where P is true, I'm missing words. Q logically follows from P is true in every sentential interpretation where P is true. Okay, that makes sense. I think I just said something weird or...
I think you were just saying it.
You're verbally wrong.
Yeah, I said something weird.
Just pulling it off.
Okay, so let's go into sentential interpretation. What's a sentential interpretation of a sentence? So a sentence P is a sentential interpretation of Q if and only if, remember the double F is if and only if, P can be obtained from Q by replacing the component atomic sentences of Q with other sentences. Now, that's kind of a mouthful, but what it means basically is we have to preserve our overall form. So if P is an implication sentence, if Q is an implication sentence, P better be an implication sentence. It better preserve the overall form. If by only replacing the atomic sentences, if I got P by only replacing atomic sentences of Q, it was a sentential interpretation. So let's look at a hard example and then we'll go over the definition here. It's pretty simple, it's just a mouthful to wrap your head around. If the sun shines, then I am happy. What are the atomic sentences there?
If
The sun
the sun
shines,
shines,
I am happy.
Right, we have two there. The sun shines, I am happy. So I'm going to make another sentence, P, that is a sentential interpretation of this sentence, Q. So here's Q, I'm going to make a sentential interpretation of it. How do I do that? I replace the atomic sentences of this with any sentences I want.
Okay.
So I replace the sun shines with Jack likes Jill and I am sad. So if the sun shines, or Jack likes Jill and I am sad, then
should be I'm happy.
Or do you have two? No.
the sky is blue. No, I'm just picking sentences.
Yeah, you can do
They're
it.
just
Wait.
random sentences.
Yeah.
Look at what happened overall structure. I started out with the sentence A implies B, and I converted to C and D implies E, right?
Yeah.
Do you see that that's what happened here?
Where's the C and D?
Yeah.
C and D
If-
is the first.
Jack
So
likes
name the
Jill
atomic
and-
sentences in here.
Okay. If Jack likes Jill and I am sad.
And I'm
And
sad. That's what
C and D.
Okay.
If Jack likes Jill and I am sad, then the sky is blue.
Yep.
If the sun shines, then I am happy. Now notice that this still has the same form as this.
Okay.
It's still just an implication, in other words.
Yeah.
Oh.
Therefore, this is a sentential interpretation of this. Now, the other way is not true. Is this a sentential interpretation of this?
No.
No, because this is an implication whose
Right.
antecedent is a conjunction.
So A would have to be a conjunction.
Yeah.
Yes. So it doesn't work.
But what if it was an or? It would have
Still doesn't work.
Okay.
It needs to preserve the overall form. It
Literally-
can add more substructure,
Right.
but the overall form needs to be preserved.
Right.
So this
So
is
if
a
you
sentential
start
interpretation of
That makes
this.
sense of how you
This
can
is
get
not
more.
a sentential interpretation of this.
From the basics, you can get more because you are adding.
Right, so imagine I told you A implies B.
Right.
If that's all I told you, it's possible that A is really a sentence like C and D.
Right.
But it's not possible that C and D.
It is not possible that C and D is just A.
Right.
I can't replace C and D with anything I want and end up with just A. I would lose that form, that structure.
Yeah, I see what you're saying, but it feels weird to me.
It is kind of weird. It's like, why would you ever want to do that? Why would you ever want to take a sentence like this and convert it into a sentence like this? That's kind of weird.
But math.
But remember when we first defined a tautology, we said if, so you have your starting sentence. If every time you replace your atomic sentences, it's still true, then it's a
As long as
tautology.
the form is.
Yeah.
If the
If
form
you're
is
only
tautology-
replacing atomic sentences, you have to leave the form,
Yeah.
Right.
right? Because replacing atomic sentences means replacing A and B. Or in this case, it means replacing C, D, and E.
So a sentential interpretation is.
So P, this one, P, the right-hand thing, is a sentential interpretation of Q, this thing, since P can be obtained from Q by replacing the component atomic sentences with other sentences.
Okay.
Makes perfect sense.
Maybe they're the same. Like I could have plugged A right back in there if I wanted. Now remember the one gotcha there is you have to replace the same sentence with the same sentence.
What?
So if I had A implies A here, when I swap out my A for this, I have to swap out this A for this as well.
Right.
Oh.
So it would be
Yeah.
C and D implies C and D.
Yeah.
Because otherwise you could lose your tautology. So for example, we know that A implies A is a tautology, whereas A implies B is not. This is always true. If A is true, then true implies true is true. If A is false, then false implies false is true. But down here, it's possible that we have A true and B false, in which case the
Oh, yeah.
multiplication is false. So this one's always true, this one isn't. So this also is not a sentential interpretation of this.
Okay. It's not.
It is not. We would have to do, we have to replace our A's with the same thing. So we would have to replace it with the same thing on both sides. Doesn't matter what you put on there, but it has to be the same thing. Make sense?
Yeah.
Okay, so that was sentential interpretation. Remember, we're just working up towards logically followables. That's what we're aiming for. So we now understood what an interpretation was. Oh, I wanted to give another example to drive the point home. So now my question is this a sentential interpretation of this?
Okay, go. Well, I already asked.
So
you.
this
No,
is.
because or. Yeah, you already.
I already
said
asked.
that.
Alright, you already got it.
Yeah, you said
So
that.
converting
doesn't
A
follow
and B
the same.
implies C to D or E implies F.
It is not.
It doesn't work, right? Because we didn't preserve all the form. We had and here and we had an or there. What if I would have done it and it would have looked like this when it was all said and done?
Well, you get a candy because that's right.
Is this a sentential interpretation of this?
No.
We got a no and a yeah.
Yeah. it
We
is.
need a tiebreaker. Huh?
Oh no, it's not. No, it's not.
Okay, he sees it. Who else sees it?
We have two ors.
Oh, A and B.
Wait. Never mind. It is Dottie.
It is.
It is. You get a
So what do we have?
What is that?
We have in the antecedent, we have the conjunction of two statements.
Yeah.
It doesn't matter that this statement's a little messier. It's still just in the antecedent we have something and something implies something.
Wow, that's
So we can add structure. We just can't get rid of the structure that we already added.
I see.
Let's try another one.
Oh, you won't give me this.
Uh-oh, a bracket.
Yeah, it's happening really big.
You forgot another bracket.
No.
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 Not.
Whoa! We have an and and an.
Nice try.
And we have implies a statement, implies
Nice
a
try.
statement.
You're so cute. You're so good.
No, it doesn't work. The antecedent is oring together two statements that happen to be conjunctions. This antecedent is anding together two statements. Good.
How would you describe an antecedent? The first
It's the left-hand part of an implication.
Yeah.
So when I have
And
A implies C,
left hand
Antecedent.
implication. Okay.
consequent is typically what's used. I'll probably say antecedent and conclusion.
Well, implication. What if it's not an implication? Antecedent is the left-hand part of the sentential.
The same way that we call the two sides of a conjunction conjuncts, we call the left-hand side of an implication an antecedent and the right-hand side a consequent. It only makes sense in the context of an implication.
Oh, implication. Only an implication.
Right.
Okay.
So if I say antecedent, you know I'm talking about
Implication.
an implication. The same way if I say a sum, you know I'm talking about the addition symbol
Yeah.
along with two numbers. Okay. So I think you guys are getting comfortable with sentential interpretation.
Keep the books for long. Sometimes there's conversation that has I forget. So we went over the two things. The sentence P. Yep. We talked about that. I had better ones.
Okay, now we're to these. Okay. So there's a sentential interpretation. And we went over this, okay, good. Okay, now 4 points to make about logically follows. So, first off, Q logically follows, I think I'm missing follows. Q logically follows from P if every sentential interpretation of P implies Q is true. If every sentential interpretation of this, so if no matter what you plug in for P and Q, it's, so we sometimes lose track of the fact that P here is a sentence. And it could also have other parts to it.
right.
So maybe
It's
P
just like a variable in
is equal to something along the lines of
Right.
X or not X and Y, and Q in this context is really equal to some other thing, right?
Mm-hmm.
So if whatever it is, as long as its main structure is an implication, just like the main structure of this thing was still an implication. So if I got something, doesn't matter how convoluted it is, whose main structure is the arrow, or in other words, overall it's an implication. However crazy that sentence is, it's still an if, blah 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 blah, then blah 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 blah. If it's of that form, then it's an implication. So if I have an implication, doesn't matter how crazy it is, and if every sentential interpretation of that implication is true, then the right-hand side logically follows from the left-hand side.
Okay, so it has to be true.
No, logic follows.
If every sentential interpretation of the implication is true, then the consequent logically follows from the antecedent.
Okay, that makes sense.
Mm-hmm.
I'm kind of confused why we said logical follows instead of just saying the implication is true. In one.
Well, you see that we're going to get to, it's an implication that's also a tautology.
Okay.
But remember how we defined tautology to begin with. We defined it in terms of these sentential interpretations. Right? Like you want to skip straight to the truth tables and do the kind of, you weren't in discrete math. You just want to get basically to the Boolean algebra. Start plugging in truth and false values and just treat them as variables and go from there. The author's working really hard to start out with. We've got sentences in plain English language. And working up to that point. So you see where he's going and you're jumping the gun. He's just trying to carefully get there from sentences to logic. And then we're good to go. Make sense?
Yeah.
Okay.
Where are we gonna go? That's
You never know.
Are we gonna continue dealing with sentences or English sentences or math?
Yeah, but we'll look at English sentences, we'll convert them, we'll symbolize them somehow, and then we'll analyze those symbolizations and come to conclusions about it.
Which are
So
gonna be
proof.
mathematical?
Yeah, you're
Yeah, we'll be doing proofs. We'll be doing.
My question is it gonna go into mathematics? Is it gonna, at the end of the book, is it gonna start dealing with?
Yes.
Mathematics.
So the first 8 chapters of the book are developing logic. The last 4 chapters of the book are foundations of mathematics. That's specifically why I chose the book. Because just this high level logic stuff is pretty.
I think you should do this as an elective over your discrete math.
No, that's true.
No, I'll be doing discrete math for sure. What I would do is people who took this class from me either over the summer or if I offered it, I'd make it like a prereq for a Western philosophy class. I do something
Well,
like
if you
that.
do that, honest, come Arthur. If I could go to the academy once a week.
I did have a student who did that.
Me?
And you, but I mean they were on their mission
Who
and
did
still
what?
showed up. I don't know if you know Blake Zitting.
Also Mark.
I was
Oh,
gonna say,
yeah,
didn't
Mark
Mark
was-
do
Oh
that?
yeah, Mark.
Mark did that for part of the mission.
Mark and then
I don't know if that
I read
overlapped his mission.
all of that first time you did it.
I don't know if Mark's overlapped his mission. It might not have.
He did it, but
Because he only did a semester. Because then he moved to Salt Lake.
Arthur has let like Lewis go.
Yeah, I know it's happened before, so that's a real possibility.
Yeah.
Western philosophy.
But I don't know if I'm gonna do more than 2 classes. And I've got these girls doing discrete math, so I'll for sure do that. And then Emma needs to take calculus, so I'll for sure do that. So I kind of maxed out my schedule. And Leah will do calculus,
What we should do over the summer next year.
so that she can show Jacob up. I have all his assignments still, so I can compare every test you take to his test and see who does better.
You will stop him. Just kidding, you won't stop him because every test we took we got 100%.
Is it?
No.
Oh.
But somehow we got 100%. So.
You say you only got 100 on the last one, but even then I still have the actual grade,
Yeah.
not the score I gave you.
No, you don't. You already told me you didn't.
Yeah, you didn't grade. You didn't grade my test.
I can. I think I might not have it anymore. Actually, I don't know. Come to think of it, because now I remember I cleaned out my desk.
I think you might have thrown away.
Yeah, I threw it away. Anyways, just take it. I'll perform him.
Those are cavities.
He was a solid B student, so
Me?
You guys.
yeah,
I was so close.
so close to B. I'm just gonna give it to you. That's all.
You know what B is? B is a C and an A.
All right.
Why is it?
So moving on. So let's see. We already talked about this one. Did we do this one?
No.
Okay.
What did you do?
Oh, so this is basically just brushing up on what we said from the previous section. A tautology is a sentence whose atomic sentential interpretations are all true. Oh, we didn't talk about atomic sentential interpretation. So up here we said a sentential interpretation, we replace sentences with sentences. An atomic one is where we just replace the atomic sentences with atomic sentences.
So we don't add anymore?
Yeah, you don't add, you don't take away, you just replace atomic with atomic.
Yeah.
Okay.
So in other words, I give you the tautology, you basically plug in true and falses, and every time it works.
Why did you define a tautology again right there?
The author brings it up a lot. Yeah, I don't like that he doesn't just give his one definition and stick to it and come back around reminders. This isn't a great textbook, it's just the only one I could find that does what I'm looking for. I even like crash course went through 2 other logic courses I found online, and they don't go anywhere hardly. They barely get into basic proofs. like stuff we'll be doing in chapter 3 and 4, and then that's where they give up. So this author goes a lot further, and he goes all the way where I wanted.
Just make your own textbook.
You really should. Just publish it.
You already told me it's 2 hours.
It's a lot of work to
It
create a
is.
textbook. It's a lot of work to type out mathematical formulas.
Oh, well, yeah.
So just that is already a pain in the butt.
You have to have someone help you, but you can
Yeah,
do
but
it.
you know what
You
you
can
want.
write it on paper and then have someone do it on them.
Would that
I know what I want.
Yeah,
I know when I like something. Just because I can tell the difference between a good cake and a bad cake doesn't mean I can cook worth anything. I just know what tastes
yeah,
good,
but
tastes
you can
bad.
find everything you like and then add your own view to it and create a better one.
Ah, yeah, so I get good lemon cake, good carrot cake. Bam, good cake.
Don't-
Basically,
could that
and then add
be-
your own recipe.
Could that qualify you for a PhD? Like, could you do that for your thesis?
Writing a textbook? I don't know, maybe for education one? I don't think that could work for a thesis. I don't know. Yeah, I don't know. I don't know what the guidelines are. Long ways away from that if I ever do it. Okay. So, this is basically just using the exact same definition that we saw from tautology from the previous section. Next, if every atomic interpretation, so atomic just means replacing atomic sentences with atomic sentences. We're not getting rid of structure, we're not adding structure. If every atomic interpretation of a sentence is true, then every sentential interpretation of a sentence is true. So, let's make sense of that. If this right here happened to be a tautology, I know it's not, but let's pretend it is. Or let's say this one. If this happened to be a tautology, even though it's not, then this would also be a tautology.
Oh, really?
Yes, that's what that's saying.
Well, that would obviously make sense.
So adding more structure, it already has enough structure basically that now it's a tautology. The structure it has now guarantees it's a tautology, and adding more substructure isn't going to change that. Because you still have something that's true or false. Oops, switch this back to an and, so that's sentential interpretation. You still have something that's true or false, and something that's true or false implies true or false. If this is always true, then this is still something that's true or false. This is still something that's true or false. And this is still something that's true or false. Right? So if this happens to already be a tautology, adding more structure isn't going to suddenly make it not a tautology anymore. So that's what this is saying. If every atomic interpretation of a sentence is true, then every sentential interpretation of a sentence is also true. So just plugging in true or false for A, B, and C here makes it always true. Then plugging true or false in for A, B, C, D, and E here will also always make it true. Do we need to see a more concrete example of that? One that actually works? Let's do a quick obvious one. So notice that this is always true. Right?
Yeah.
Right.
Now what should I replace X with?
A and B.
So if I come along now and I say A and B or not A and B. If this was always true, then this is definitely always true as well.
Right.
Make sense?
No.
No?
Well, it's going to reduce down.
If this is true, then this is false. Right?
And false.
If this is false, then this is true.
Yep.
Make sense? And that's an or. So true or false is always true. You see how the top one's always true?
Yeah.
So this one's always true. Now let's look down here.
A and B is not always true.
Now, but if A and B is true, not A and B is
False.
so A and B or not A and B is
True.
true. If A and B is false, then not A and B.
It's true.
You see how this is really just saying the same thing as that?
Yeah, I was looking at A and B only. Yeah, I was looking at the first part only.
Okay. So that's what it's saying. If this is always true, then this is always true. You don't have to do the work. And it doesn't matter what you plug in for X, as long as you're plugging in for both X's. You can't cheat and plug something in for X and something different for that X. Make sense?
Mm-hmm.
Okay. And then finally, to put it all in simple terms, so we're going to say Q logically follows from P if and only if P implies Q is a tautology. And that's the way that we're going to reference it from here on out. What does it mean for P to logically imply Q? It means P implies Q is a tautology. It's always true. It's always the case that if P is true, Q is true. That's what it means to logically imply.
So that's
Or
a
logically
definition.
follow.
Or logically follow. Sorry, yes. Logically follow is the same thing as tautologically imply. So that's what we mean here. So given a set of premises, the rules of logical derivation must permit us to infer only those conclusions which logically follow from the premises. In other words, the premises have to tautologically imply the conclusion that we're talking about.
So the premises have to be true, therefore.
It has to be the case that if the premises are true, then the conclusion is true, is always true.
Right.
You see that? Okay,
Now for Peter.
now for Peter. He knew this day was coming. Okay,
Oh, yeah.
so let's do some basic proofs now. So now we're going to get our foot in the door with proofs. Now we're going to stick our foot in the door with actually doing logical inference. And do our first one. So premise one. In other words, we're going to assume this is true.
Oh.
Either Mary gives Peter his toy or Peter cries. We're giving that as a premise. We're saying that's true. Premise two. Mary does not give Peter his toy. What can you conclude from those two sentences?
Okay, either Mary gives Peter his toy, or Peter cries. Right. Conclusion, Peter cries.
Conclusion. Peter cries. And that should hopefully appeal to your intuition.
Right.
Right? So let's write out the truth table showing this explicitly. So M is Mary gives Peter his toy.
Either Mary gives Peter.
No.
No, just Mary.
We're doing
Peter
our
is
atomic
part of the whole.
sentences.
Oh, yeah, yeah.
So notice that, so this is often going to be the case that our premises are these compound sentences. Sentences with sentential connectives. So it's not very often going to be the case that our premises are just atomic sentences. Does that make sense what I'm trying to say?
Yeah.
So we need to identify all the atomic sentences of all our premises. So we have, from this first one we have Mary gives Peter his toy and Peter cries. From the second one we have Mary gives Peter his toy. Those are our atomic sentences, so there's only two of them. So
Right.
M is Mary gives Peter his toy, P is Peter cries. Here's what we're ultimately trying to show is a tautology. We're trying to show that if the first premise is true and the second premise is true, then our conclusion is true.
Mm-hmm.
We're trying to show that these two premises, this and this, 1 and 2, 1 and 2, tautologically imply the conclusion
Oh.
that.
Right.
Not.
Yeah, Mary does not give Peter his toy. M is Mary gives Peter his toy.
Oh, I was reading conclusion, Peter cries as part of two.
Oh no,
That is so
that's a
okay.
separate one.
This is kind of what you actually did in the first one, just less in the exercise. You started doing this because it went through a lot of you just go through the letters and see if it's true or not, and you decide if the end result is true. So I was just
Yeah, a good textbook will do that. They'll give the students exercises that have them derive stuff that they're then going to derive for them in the next chapter.
Yeah, calculus.
Yeah, you never did it.
Yeah,
Never.
because
Good textbook, bad
oh, you
student.
want me to teach myself? Okay. Shut up.
Want you to
Don't
struggle
even
to
talk
learn.
about that.
Alright, so if M's true and P's true, M or P is
True.
true. Here it's,
true,
here it's,
True.
here it's.
false.
Wonderful. Not M is just the not of N. So
False,
False.
false.
not true is false, not true is false, true, true. Right?
Yeah.
So now we're taking the conjunction of these two. Right? We're doing M or P
Right.
and not n. So M or P and not n. So true or false is, or
False.
true and false is
False.
false. True and false is false. True and true is true. False and true is false. Good? Now remember what I told you is that the author isn't going to bother writing out these last columns. He's just going to say, if every time the antecedent is true, that's right here, the conclusion is true, yep, then it's a tautology. But we'll manually write it out to make sure we see it.
Well, that
So-
made more sense than over there.
Yeah.
Goodness, Donnie.
What?
The conclusion, when you say then, if you talk about the conclusion, then yes, it makes sense. But when James and I were having issues with you trying to explain over there,
When you were like,
because you were like, when
You're
this
like,
false
all
is
of
true,
them.
this false is true and everything, he was.
You're like, every time this is true,
Yeah.
you do
This
the
time
whole.
you say the
I'm not
conclusion
sure what
is
I
true,
said.
then it makes sense.
But that's why you just keep talking. You'll eventually say it right, right?
Makes way more
Alright.
sense now.
features.
Wonderful. If it makes sense, I'm happy. So, the antecedent is false, the conclusion's true, so it's
True.
true. False implies true is true. False implies false is
True.
Just shut up. I didn't say it.
Just shut up. Wow. You come to my house. Alright. True implies true is
True.
true. And then false implies false is
True.
false.
True.
Got it.
Okay. So it's a tautology. Alright.
Weird.
So we can now use the rule if you know A or B is true and you know not A is true, then B is true. That's what we just showed.
Right.
We showed that this is a tautology. So we're over here, we're making our rules for logical inference. Here's the rule that we're about to use. Every time the antecedent is true or our premise is true, our conclusion was true. So this doesn't violate rule 1, right? We're still keeping up with that criterion.
Wait.
Every time the antecedent is true.
We just really showed that every time this is true, this is true.
That specific one.
Well, we handled all the cases.
For that specific
Wait.
antecedent.
That means it's tautologically.
So anytime you have something of the form A
Oh.
or B and not A, then you can conclude B. So for example, say I tell you Donnie's holding a blue or black marker and Donnie's not holding a black marker. You can now safely conclude Donnie's holding a blue marker. Pick any statements you want, A and B. Plug them in here. Plug them in so that your antecedent is true. Then your conclusion will be true.
Right.
Does that make sense what I'm saying?
Yeah.
So this is now a valid rule of logical inference.
And it's a tautological.
It's a tautological implication. So in other words, B logically follows from these premises.
B will always be true.
If the antecedent is true, B will be true.
Well,
For
the
that.
antecedent will always be true.
No, no, no.
Yeah.
Look at the
That's
antecedent is
just
false,
one.
false, and false. There are combinations that can make the antecedent false.
Right.
Combinations. That's
The implication is always true. But a better way to think about it, instead of thinking the implication is always true, think every time the antecedent is true, the consequent is true.
Right.
That's what we care about. Now, it just so happens that if this is false, the whole thing's also true. But if this piece is true, then this piece is true. Since the whole thing's always true. When you have a logical implication, if the left-hand side is true, the right-hand side has to be true. If the antecedent is true, the consequent has to be true.
Yeah.
If I say, if Donnie's wearing his shoes, he's standing up, it has to be the case that if I'm wearing my shoes, I'm standing up. If the antecedent is true, the consequent has to be true. Otherwise, the implication is false. And we know that the implication is always true. Sorry, I'm just trying to say it 100 ways until it makes sense.
No,
that combination.
Pick any two sentences you want of the form A and B. Pick
And
any two
that's-
sentences for A and B such that such that A or B and not A is true. So pick any two sentences you want. If I know that whatever one you picked for A and whatever one you picked for B, if I know that it's the case that A or B is true and not A is true, then I know for sure that B is also true.
Yep.
You can set up scenarios where this is false. Okay, I don't care. What I'm saying is, every time this is true, I know that this is true.
Yep.
Therefore, this logically follows from this.
Yep.
Every time the antecedent is true, the consequent is true.
Wasn't that your definition last time for something for dissentential something? I remember you talking about that. The antecedent, if the antecedent is true, then the consequence is always true.
Well, isn't that
Wasn't
just?
that like
That's when an
definition?
implication is true.
That's an
I'm
implication.
saying,
When an implication is true, then the antecedent being true
Okay.
means the consequent is true. That's why we need the implication to be a tautology. A tautology is always true. So in other words, if I have an implication that's guaranteed to be true, then if the antecedent is true, then the consequent is true. That's what we're saying. Right?
Mhm.
So pick any sentences you want, A and B. As long as they satisfy our premise, then our conclusion is guaranteed. Okay?
only for that combination.
In this case, yes, this is one rule. Right? And it already made intuitive sense to you. You already knew how to use a rule in your head. You've done this tons of times in your life. Right? If you're outside the classroom and you were to think in your head, I know he's on the left-hand side of the classroom or he's on the right-hand side of the classroom. And you open the door so you can only see the left-hand side of the classroom and you can't see me, you instantly know I'm on the right-hand side of the classroom. Right?
No, you're in the bathroom. That's
Well, I'm saying in case we knew.
yeah.
Or me and you go out and we go get some food. We both go and get subs. You got an Italian, I got a BLT. We go put them in the fridge. You go to the fridge later. You can't remember which bag was yours. You look in one, and you say, oh, it's the BLT. So you grab the other bag and you walk off. You know that yours is the other bag.
Yeah.
You know that yours was this bag or this bag, and it wasn't this bag.
Yeah.
Therefore, it was this bag. You do this all the time. Simple logic.
How do people use that form wrongly? Like, can you use that?
Well, we'll get to an example of,
fault or
we'll do one that people often do is wrong, but first let's do this one. So let's look at, if I know B and A implies B, do I know A? That's a tautology, right? Do we have to spell this one out for you? Can you just see it?
Give us 1 second.
If I know B and I know A implies B, obviously A is true.
Oh, obviously. Yeah.
Oh, obviously. No!
Yes, huh?
No, and let's go over it.
Look, if B
So
is true.
now I'm going to pick a sentential interpretation. That satisfies the premises. Alright. B. I'm in the United States. Is that true?
Yes.
Yes. A implies B. If I'm in Alaska, am I in the United States?
Yes.
Can you conclude I'm in Alaska?
No.
What? It satisfied the premise. I found two statements A and B, such that B was true and A implies B is true, and yet A was false.
Okay. Yeah.
So this is a bad rule of logic. We can't use it. It violates Criterion 1. Criterion 1 says we can only get those conclusions which logically follow from our premises. You guys see how this is a bad rule of logic? I'm not in Alaska. I'm right here.
Too bad.
Pretty close.
So you can conclude that you're in the United States.
Yeah.
If I'm in the United States, you can conclude I'm in the United States? Yeah, you just gave us X implies X.
no, if you're in Alaska.
Oh, yeah. So now, that's exactly right. So that's the next one. So I said, what about if we know this? What about if we know I'm in Alaska, and if I'm in Alaska, then I'm in the United States.
Yeah.
Can you conclude I'm in the United
Your
States?
whole
Yes.
point
That
is,
makes more sense.
on the one case, everything's true. On your antecedent.
This is not a logical tautology.
Wait, yeah, if Which one? Okay, no. Yeah, no.
How do I show that this is not a logical tautology?
You plug in your
Or
You make
logical tautology.
logic
How
follows.
this is not a tautological implication. This implication is not always true. How do you show that an implication is false? You find a case where the antecedent is true and the conclusion is false.
Yeah.
Remember the truth table for an implication?
Yeah,
True implies false is
false.
false. So if I can get true implies false,
Then it is false.
then it's false. Now I took the time to write out sentences here, but it doesn't matter.
That
I could have
makes
just plugged
sense. Okay, that makes sense.
In the truth table.
I could have just plugged in true and false implies true does not imply false,
Right.
right?
Right.
But I picked actual sentences that happen to be true and
Right.
false the way that I want to plug them in. But the point is, this is a valid sentential interpretation of this, and it wasn't true. Therefore, this is not a tautology.
Right.
Make sense? And then this one is a tautology. If I know A, and I know A implies B, then I know B. If I know Donnie's holding a black marker, and if Donnie's holding a black marker, Donnie's holding a blue marker, then I for sure know Donnie's holding a blue marker. If I know it's raining outside, and I know if it's raining outside, then there's clouds in the sky, I know there's clouds in the sky. Another basic one we do all the time, right?
Right.
Whew. All right, 3 hours later, and we know 2 rules for logical implication.
Remember how we
2
tried
hours
to teach
later.
us some last
Hour,
time?
yeah, hour and 15 minutes.
I'm just joking.
Got it.
So,
Hey, Donnie, I have a question.
go ahead.
What's a criterion?
Criterion. It's the singular for criteria.
No, I'm mostly making fun of your question.
What about criterion 2?
Yeah.
So last one I was going to go back and have the conversation we had at the start. What about this one? So I was going to come back and say, okay, so we found ones that work for this, but what about criterion 2? Why did we need to say, given a set of premises, the rules of logic derivation must permit us to infer all those conclusions which logically follow, because this doesn't get us anywhere.
What does that?
Whereas this and this start giving us new information.
Right.
Huh?
What does that criteria come from?
These are our 2 criterion
For what?
for what we want the rules of logical derivation to do.
Oh,
This is so we can build off our premises.
okay.
So as we're building our rules for logic, we want them to satisfy these 2 things.
Okay.
Good?
Mhm.
Okay. So that was the end of the first section.
Section?
Yep.
How many sections
We
are
do
in
it in
chapter?
sections.
4 in this one, but section 1 had all the meat of everything. From there on out, the other ones are just basically doing examples. I need to get some water. You guys can start looking at those exercises, see if there's one you want to do. Huh?
No, she needed water.
Yeah, my throat is dry.
Take specific counterexamples for the following 2.
Collacious rules.
What does that mean?
No idea.
Wait, are we already at the end of the chapter? Or does it start doing exercise at the end of each section?
What does
Collacious
correlations
rules.
rules?
Sorry, what?
Fallacy, yeah, it's a fallacy, that's what I thought.
Oh, a fallacy? A fallacy is like a bad piece of reasoning, a logical fallacy.
Yeah.
So you could call this one that we did right here a logical fallacy.
Right, we'll say, you know,
What do you think?
it's a logical fallacy.
So an example of logical fallacy would be only guys play in the NFL, Jacob's a guy, therefore he plays in the NFL.
Yeah.
People use logical fallacy sometimes. And don't
I
realize it.
use the logic fallacy just barely.
Yeah, when you guys all agreed that this was true.
Hey, that's not my
When you
fault.
flat out were talking about logical fallacy, classifying it as true. You have to use bad logic to classify bad logic as good logic.
So are these exercises that you actually want to do? Is it doing exercises at the end of each section?
Some
Instead
sections,
of-
some sections don't have any. So none of them look good
That's
to you?
like all last chapter, all those exercises were at the end of the chapter. Section.
None? You just want to continue?
6.
I wonder if these like.
6?
Yeah.
Alright. Which of the following sentences are sentential interpretation of the sentence, I lost track, of the sentence, it is raining or it is snowing? Okay, so we want sentential interpretations of it is raining or it is snowing. Let's just write that out real quick. So we have a sentence, it is raining or it is snowing. So if we were to identify tautomic sentences and symbolize it, it'd look like this. Okay? So now, which of them are sentential interpretations? If it is raining, then
It's
it
gonna
is
be
snowing.
either. Could be either. Oh wait.
Ew, that one's tricky.
What?
Is the statement, if it is raining, then it is snowing, a sentential interpretation of this?
It loses
No.
its form.
It actually is.
One second.
Now here's the trick.
Or it's no.
This is, I can't remember if we went over this one or not, but A or B is the same thing as not A or B. Oh,
That's
so
not what
sorry.
it's saying.
It's not.
No. Sorry.
It's not A and B.
Sorry, I didn't mean to do that. A implies B is the same thing as not A or B. So not A or B is a sentential interpretation of A or B, right?
Yes.
Yeah.
This is a sentential interpretation of this, and this is really the same thing as this, it's just in disguise. So remember, your implications can always be phrased in terms of force.
Oh.
It's
One
D.
big,
So
Wait.
it's saying
Let's
if it is raining.
write
then
this out one more time.
it is
Sorry,
snowing.
but there's no not. There's no not in that.
A,
he's saying there doesn't have to
B.
be because therefore it basically
It's the
implies
same
B is the
thing
same
as
thing.
not A or
As
B.
not A or B, which is a sentential
A
interpretation
implies
of
B.
A
So let's look at this real quick.
or
True, true, false, false, true, false, true, false. Okay. Not A or B. So false or true is
True.
true. False or false is
False.
true or true is,
True.
and true or false is.
True.
You know why I'm saying the opposite thing here?
Yeah.
Yeah.
There's a not there, not A, so I'm just skipping a step. Okay, now it's the implication. True implies true is,
True.
true implies false is,
False.
false implies true is,
True.
false implies false is.
True.
What?
So A implies B is the same thing as not A or B. So if I have A or B, not A or B is a sentential interpretation of that, right?
Okay,
Yeah.
but guess what? It's not.
Which is the same thing as A implies B.
Okay, but it's A implies B.
A
It's
implies B.
basically skip that middle one.
It doesn't
Yeah.
matter.
Because it's the same thing as it.
This is the same thing written two different ways. There's no difference.
What I'm saying is, in our specific number 6 example, it is not anything. We're nodding nothing.
You could add on for
It is
sentential
raining or
connecting
it is snowing, right?
or interpretation.
It is not raining or it is snowing. Is that a sentential interpretation?
Yeah.
Yeah.
That's not what it's saying though.
If it is raining, then it is snowing.
I
Is
just don't
the
get
exact same thing. If A then B is identical. There's no difference between if A then B and not A or B.
you just ruined your form though.
Yeah, you did.
You ruined your form.
It's the same thing encoded a different way. You guys are getting mad
You're still
because
getting
the
too
answer's
fast.
supposed to be 6 and I wrote this. And you're losing your minds.
Well, I'm saying, okay, that makes
3
no,
plus 3
no
equals 3
absolute
plus
sense.
3.
Because think about the actual sentence.
No, six equals
If it is raining,
Yeah.
it does not mean it is snowing.
If it is raining, then it is snowing. Okay. You're saying it raining and it snowing have nothing to do with each other?
Yeah.
Okay.
So if it is raining, then You cannot.
It is not raining or it is snowing. Do those have anything to do with each other? Let's assume that this statement's true. If it is raining, then it's snowing. Let's assume that's true for a second. Okay? What does that mean?
It means every time it's raining, it's snowing.
It means if you know it's raining, you know it's snowing.
Right. Right.
But what if it's not raining? Could it still be snowing?
Yes.
Yeah, we don't care in that case.
Okay.
So we know one of two things. We know either it's not raining or it is snowing, if that statement's true.
Yeah.
So we know it's not raining or it's snowing. I don't know why that clicks better than the truth table, but
That is so cool.
and that's actually how some textbooks choose to define this. They to prevent themselves from having to have the conversation about vacuously true weird applications. They just want to say we define this to mean this, and then continue on their merry way.
That's nice.
I don't
Not
like
A
it.
or B.
Okay, so we're all good with A on number 6. Right? Alright, B. It is snowing. Is that a sentential interpretation?
No.
No. It is snowing or it is snowing. Is that a sentential interpretation?
It lost its form.
No.
It lost its form because it's A or A instead of A or B.
Yes.
Is there something wrong with it?
No.
Yes.
I'm confused
Well,
on
It
what.
lost
Not
its form.
really.
It is
Oh,
fine.
oh.
It replaced every occurrence of
A.
Atomic
B.
sentences.
with something. In this case, it happened to be A. Look, if A or B was true, is A or A guaranteed to be true? No. That is weird.
Yeah. Because they,
Donnie, you literally
You
said
had two
you
statements
said
of
when
the
we were
form.
talking
That
about
is
that.
always true. Oh, always true. So even when B was false, it happened to be true. Okay, so no, it works. So if this statement is always true, no matter what truth values you assign to A and B, if A and B are of the form that no matter what truth values you assign, this is always true, then that means even when this is false, this is true, and even when this is false, this is true. No, because B could have just been tautology by itself. Because we should have had something of the form false or X or not X. Because A or A, oh, yeah, it's not. Okay, here's how we know it's not. You do this form. You guys were right to begin with. A or A is the same thing as A. So you replace A or B with just A.
So it's
Yeah.
not.
So you can't or a statement with itself.
Yeah.
Because then you lose form, because then you just have the
Yeah,
statement.
and the
Right.
statement itself.
Ending a statement with itself,
I thought that's what we said right there. I thought we were saying.
you have the same problem.
I thought you were saying.
Because
yeah.
A and A
we
is
were
just
talking
A.
about or though.
So,
I thought you were saying no, that you can't make A or B be A or A.
not
I thought that's what you said.
A, but not A.
so yeah, I can't replace A or B with just A or A, because then you lose the or.
Yeah.
Because then it's just A.
A then A then not
So yeah, that's right.
A then definitely
Okay, it is snowing or it is snowing. Okay, no. It is snowing or it is raining.
Yes.
Yes.
Either it is snowing and it is raining, or it is not raining. Yes. The either at the beginning lets you know
It's not
that the
either.
outer structure is an or.
Right.
A.
So it's saying either this
Right.
or this.
PEMDAS, what was it again? Or and comes first. If the
And.
either wasn't there.
And comes from.
Oh, that's only when you're writing it out how I have it written out. When it comes to an English sentence, you just have to understand how to interpret the English sentence. So that does bring up a point that we should probably make. There's not always a way to take a sentence and convert it into logical symbols correctly. There are some sentences that there's just as much reason to interpret one way as another way. Like deciding, are we doing an or then an and, or an and then an or? Some sentences, the way that they're phrased, there's no way to know which of those is a better
If
interpretation.
this one would have just said, where did it go? It is snowing and it is raining, or it is not raining.
With no commas, nothing,
Right.
then yeah, that's kind of hard to know what they're after. So the point was, we can't always go from an English sentence to symbolization. But 100% of the time, we can go from symbolization to an English sentence. So we always know how to interpret the symbols with English. We don't always know how to interpret the English with symbols. Symbols are very precise. We know exactly what we mean by them. English is inherently vague sometimes. Good? Okay. So we went through 6.
That was a good one to choose. You're so good.
Amazing. Except for you didn't get the only trick question on there, which was the implication.
Got it? As soon as you explained it.
Teacher said you didn't get the answer right. Yeah, I did. As soon as I looked at Peter's paper, I wrote it down perfect.
If yours is
What do you
correct.
mean?
Missing that point.
Alright. So, continuing. Alright. So now, sentential rules of derivation. So now we're going to get into proofs. We're going to start out with some sentence. We're going to symbolize it or codify it like this into premises, and we're going to determine if the conclusion logically follows. Maybe it's better to just jump into an example and then go over these rules. So let's just jump into an example right out the door and go over a proof.
Yeah, this board isn't too much worse than what we had going in the calculus room.
Oh, it's way worse.
No, it's in the calculus room?
Oh, in the calculus room I had a good board and a bad board.
Or do you even get this board?
Jacob got it. Oh well, we don't need all the space. Okay. So, let's go over the example. We'll come up with ways to codify it as we go. So,
Holy cow, that is intense.
our first sentence. If there are no government subsidies of agriculture, then there are government controls of agriculture. So I'm going to say that is, if there's no subsidies, that implies there's controls. Good?
No,
Yes.
if there is,
No,
No
subsidies implies government controls.
Right.
So that's what the first sentence says. Okay? And I'm going to do some other stuff on the side as we do this. I'm going to say this was a premise, and the only thing it depends on logically is itself. So I'm going to do a set with 1 over here, because this was line 1. 2. You'll get these other things as we go. It's just kind of like, you remember like doing T-table proofs in geometry?
Yeah.
Yeah, kind of the same thing. So we're going to do the
Yeah.
line of our proof.
Yeah.
Here we're going to state if it's a premise or how it logically follows, which lines it logically follows from. And then here we're going to keep track of all the premises it depends on. Okay. Next. If there are government controls, there is not a depression. So controls implies not a depression. You with me on that?
Yeah.
So that's a 2, that's a premise, and it only depends on itself.
Oh, I see why you say premises, because eventually they'll start using each other. I see.
Yeah, the last sentence
Yeah,
of this is going to be a
go to,
conclusion, and we're going to see if it logically follows or not. Make sense?
I love how you don't even need to know what all this practice.
Yeah. I think he's intentionally picking these things like, what? To make you wonder a little bit. And then you realize, oh, I don't care.
Yeah.
Okay.
If there, we already did that one.
There is either an agricultural depression or overproduction. Make sure I don't miss my notes.
Holy crap,
There's either an agricultural depression or an overproduction. So
We
3
did not have this logic class.
is we have a
We would not
depression
be able to say.
or an overproduction. That's a premise. It only depends on itself. As a matter of fact, there is no overproduction. So 4 is not an overproduction.
Right.
And again, it's a premise, and it only depends on itself. 5, therefore, there are government subsidies of agriculture. So we're trying to prove S is true. There are subsidies. So that's what we're trying to get to. These are our premises. You good?
Wow, that's
But
a
the
lot.
only way to prove that S is true is if you prove that it's a tautological. Tautological.
These are all premises. I know that all these are true. I need to show that these imply this is a tautology. Now, one way I can do that is I can draw out a big, massive truth table,
Or just look for the truth.
which becomes impractical as these get bigger, right? How many rows do I need in a truth table if I only have one variable?
1.
How many rows do I need in a truth table if I only have one variable?
4.
2. There's only 2 cases. The variable's true or the variable's false.
Rows.
I see with columns.
If I have 2 variables, how many rows do I need?
4.
4. Because I could have true, 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 false, false, true, false, false.
Right.
If I have 3 variables, how many rows do I need? 8. I could have true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false,
Right.
false, false. Did I miss one? I don't know. There's 8 of them. If I have 4 variables, how many rows do I have?
16.
If I have 5 rows, how many 5 variables, how many rows?
32.
If I have 20 variables, how many rows do I have?
Don't do that to me. You said 10 last time.
Over 1 million.
Yeah, don't attempt that, please.
Yeah, not smart. So, it's not practical to come up with a truth table for showing that these tautologically imply this, even though at this stage we can. We're going to find out later as we introduce more rules for our logic that it doesn't work. But for these basic things we can, but it's even impractical then, and once we have more to our logic, we just can't come that point.
So
anyways.
what we're going to try to do is try to create a tautological.
So we're going to
statement.
use tautologies. We're going to use our rules. We know that if this is true, this is true. We know that this tautologically implies this. So if we have something like this in our, if this is a premise and this is a premise, we can conclude that.
Oh, so we're going
Right.
to use our or. Oh, that's an it.
So we're trying to include S. So let's see. I know D or O is true, and I know O is false.
Right, no.
Uh-huh.
So what do I know about D?
It's
It's true.
false.
It's true.
It's true.
It's true.
If D or O is true
And
And
O is
O
and
is
O is
false.
false,
That has to be true.
then D is true. So what do I do right here? I say 5. I can now conclude D, and that was tautologically implied by 3 and 4. And so now this depends on premises 3 and 4.
Wait, why did you just put D down? Like,
I now know D is true. This is now a true. I'm
We're
writing down
missing
statements
all
I know
our
are true.
truths.
I know this is true, it was a premise. I know this is true, it was a premise. I know this is true, I know this is true. Now I know this is true.
Okay.
The better way to say that is, I know that these premises imply this is true. That's what I should say. We assume our premises are true. We don't really know they are true. Think back to the axioms of geometry.
You don't see false.
You don't know that those axioms are true. It's
C
just
is
if
true.
those are true.
C
All
has
of
to
you
be
fighting
false.
geometry.
C is true.
C has to
Not
be
D.
not
D
D
is
false.
true. D
C is
true,
false.
so
C
not
is false.
C
Because
is
the only
false.
way that implication can be true is if false implies false. True
So-
can't imply false and come out true.
Oh, yeah.
So we know not C. This is tautologically implied by 5 and 2. So now we're using premises 2, 3, and 4. And let's make sure that this one makes perfect sense. So we're saying that we're concluding 6 from 5 and 2, right? So I know if C is true, then D is false.
Well,
But D is true.
So C is false.
So C has to be false, because if C is true, then D is false. That's one way to do it. Another way to do it is,
Oh my goodness.
here's A implies B,
Oh,
right? We already have it done. That's the same thing as not B implies not A. It's called the contrapositive.
Yeah.
Not B implies not A.
I didn't do
So
that.
false implies false is
True.
true. Oh, sorry. True implies false is
False.
false. False implies true is
True.
true implies true is
True.
So that's
they're true in the exact same cases, so they're the same way of doing it. So rethink of 2 as D implies not C.
No, D implies
Oh,
C.
oops.
D implies C.
No.
Oh no, I did
D
that right.
implies not C.
yeah.
Not this thing. What's not D?
Right.
Just D. Implies not this thing. What's not C?
Right.
It's not C. So I knew D, and I knew from 2, this and this are the same way as saying 2. So I knew D, and I knew D implies not C, therefore I know not C. Make sense?
Yeah.
Alright. Wonderful. Okay, so now we got not C,
And then same thing.
and then the same thing with this one. Not C implies S.
Well, not S implies C. Or
No.
not C
Not
implies
C
S.
implies S.
Not C implies S, and I have not C. So now I know S. That's tautologically implied by 6
Sorry.
and 1. And so I've used premises 1, 2,
It's
3,
exactly the same
Therefore-
thing.
4.
No, very different because first we're dealing with the, what's it called, the one before Aston.
What?
It's not the same thing in my head.
What's not the same thing as what?
We implied not C because C was the one that came first before the implication. Now C is your,
You're saying getting this line,
yeah, no, yes.
or getting this one?
Getting 6 is not the same as getting 7.
Yeah, it is. So 6 we got from, we knew D was true.
Right.
And we knew that C implied not D was true.
Right.
C implies not D can be rewritten as D implies not C. So we knew D, and we knew D implies not C, therefore we know not C.
Okay, now do
Here,
the
wait.
Now
so
do the other one. Not S implies C is the same thing as not C implies S. We know not C, and we know not C implies S, therefore we know S. Because you just flip them around and nod them both. It doesn't matter that they already had knots to begin with.
Right.
Right.
So 2 knots makes it.
Oh yeah, we didn't talk about double negative. Do we need to prove that double negative?
Is positive. No.
It's true.
A double negation is the same as doing no negation. So yeah, I guess I am doing that behind the scenes. Anyways, so there we go. There's a proof. We just really proved that that is the case.
Oh, because we got S.
Because we got S. That's what we were after. Now,
So what's S?
this was the exact same thing as if you would have done this truth table for this. If I said construct the truth table for
Oh, just ands in between all these.
yeah. Oh, that's it. Maybe I'll put parentheses on this one.
Wow, we are already scientists,
Scientists.
mathematicians.
So I could have said to you,
Scientists.
show that this is a tautology, And you could have constructed a truth table, handling every possible combination, showing that this is always true. Or you could have done it this way. Okay?
I like
So
it.
this is what we're going to refer to as a logical derivation. Alright? And now we're going to look at the rules real quick that I said that we could use. I said it'd be better if we saw an example, then we'll look at the rules. So there's 3 rules. Rule number 1 we call rule P, because it has to do with premises. You'll notice I put P's here. We may introduce a premise at any point in our derivation.
Yes, that makes sense. Because look,
Yeah, you can add a premise anytime you want, because what you're showing is that when you do a derivation, you're showing that your premises imply something.
Based off this.
You can add more premises all you want, you're just showing that those premises imply something. We show that this is logically follows from 1, 2, 3, and 4. Maybe I use a premise, maybe I don't. But I now know that this depends on these 4 premises, and if these 4 premises are true, this is true. Notice this didn't depend on all 4 of them. If they just want me to prove not C, I only needed these 3 premises. I didn't need premise number 1.
right.
And similarly, if they just want me to prove D, all I needed were these premises.
Right.
Right?
But you got C using 6 and 5, so you used all of them, right? And you got S, finally.
Yeah, so what the problem is saying is using these premises show that they logically imply this. So I can't go around just adding premises that the problem didn't want me to use and say that I showed it. Right? Okay. So you can introduce premises at any point. Rule T because it has to do with tautological implications. That's what we used here, here, and here. Rule T, we may introduce sentence S, some new line, like this line. We may introduce some new line, or some sentence S, if there are preceding sentences whose conjunction tautologically imply S. So I could add not C, because there are sentences, namely sentence 5 and sentence 2, whose conjunction tautologically imply it. That's what I was saying. I was saying that not C was tautologically implied by 5 and 2.
Dude, the way I thought about that was literally true implies false is false. Therefore, C has to be not C.
Well, you can come to conclusions about it that way. You can think about, I know C is false, and I know an implication.
I was talking about the number 2.
This one?
Yeah, so we know D is true.
So you know D is true,
Right,
and you know that if C is true, D is false.
right.
And since D is true, C can't be true. Yeah, you can use that kind of thinking. So one of the points the author makes is, so we're going to go over some basic tautologies that you use as a general rule. And some of them have fancy Latin names, so you can use their Latin name if you want to sound cool. Like, a common one that we went over all the time was reductio ad absurdum,
Nice.
proof by contradiction. So they have their Latin names, and the ones that are used a lot get Latin names because they're common tautologies, but any tautology you use is perfectly valid. You don't have to use given tautologies. And in fact, we didn't even really write out exactly what tautologies we were using here. We just kind of thought about it and realized. But we'll get into the list of tautologies later. Anyways, so ultimately that's what we did. We showed that this thing is a tautology. This big beast here, right?
So, no matter what,
As long as you pick sentences S, C, D, and O, such that this premise is true, then this conclusion will always be true. In other words, it doesn't matter what truth values you assign to all these, as long as you make sure that the premises are true, then you will have also made S true.
so
There's no way to make this whole thing true without making S true. If this thing is true, S is true.
the nice.
Tautological implication. The antecedent is true, consequence is true.
Yes.
Yeah. So there was an example. Not bad, right? Actually kind of fun.
What's
Yeah.
S?
You just have
F's? Who knows?
There's no
The government, therefore there are government subsidies of agriculture. Now notice, we did not prove that there are government subsidies of agriculture is true. All we showed is that the premise implied it's true. Maybe the premise is false.
Right, it starts with if.
Remember, if the antecedent's false, the implication's still true.
What subsidies?
Basically,
Don't tell me no.
no. A subsidy is when the government's helping pay for it or you're getting some sort of break for it.
Hey, I know
So,
what
for
that is.
example,
In India.
if you pay private insurance, you're basically subsidizing people on Medicaid or Medicare, because what happens?
It's like a money.
Medicaid and Medicare will only pay for so much, so hospitals have to undercharge them, and then they have to overcharge private insurers so that they can break even.
You told me about this.
So if you have private insurance, you're also paying for people on Medicaid and Medicare indirectly. You're basically subsidizing them. You're paying part of their share of it. It's why people who think that you can just, let's do everyone on Medicaid and Medicare are retarded. The only reason that the Medicaid and Medicare system is working right now is because people have private insurance and are paying for it. So if everyone was, suddenly it's not getting paid for anymore. And hospitals either have to start charging more, or the system's broken.
I vote two.
Or more tax money has to go in. Well, I vote just get rid of them. It's retarded. Because private insurance could go down, because it's just trying to be as competitive as it can, if they didn't have to be charging more.
Darn hospitals are charging more.
Yeah, because it's so messed up. There's no way for me to go into a hospital and say, this is a procedure I need now, how much is it going to cost me? They can't answer that. They have to know my insurance. They have to work it out that way.
That is really stupid.
Yeah, so you have no clue what you're going to be paying for some hospital visit.
Like
Until
my
after the
insurance or my surgery was gonna cost like $7,000, and because my insurance only cost like $1,700. It's really weird. It depends on
Yeah,
my
I'm sure that
insurance.
that was somehow through Medicaid or Medicare. Because, like, my deductible on my insurance, I think is $5,000. So I have to pay $5,000 out of pocket before my insurance even kicks in to start covering it. And I have relatively good insurance compared to a lot of people. Because I don't qualify for Medicaid and Medicare because I don't make little enough. So if you make too much money, then you can't qualify for those programs because they're intended for people who can't afford their own health care. Anyways, so that's what subsidies. Yes, these sentences make perfect sense to me. And I can explain all of them to you if you want.
Are you
Then
serious?
there are government controls of agriculture.
If there are
Then
no
there are
government
government-
subsidies of agriculture,
If there are government
then there
controls.
are government
There's
controls.
no
Okay, what does it
agriculture.
mean to have government controls of agriculture?
So for a government to have controls in an economic system is their way of trying to control a supply and a demand. So artificially keeping prices up or down as needed.
By them subsidizing, it gives them kind of more control.
Well, subsidizing is kind of like saying now you're going to get more than what the market would bear for what you're paying. If for a farmer, if you're subsidizing their agriculture, so either they're going to give them a tax break because of it, or they're going to say, well, most likely it's going to come in the form of a tax break, but basically they're saying we're going to give you $10 for every acre that you do, plus what you actually sell it for. So it's a way of encouraging them to keep doing it.
Right.
Because maybe if they did it, so maybe I'm selling something, and if I sell it, I'm going to lose $2, but the government really wants me to keep doing it, so they say, actually, we'll subsidize you $3 for everyone you sell. So now I'm making $1 profit, even though without them I wouldn't be.
This is
It's a way of keeping
really
the
funny.
competitive market going.
There is either an agriculture depression or overproduction. As a matter of fact, there is no overproduction. Therefore,
Alright,
this
So there's his proof. We probably did it identical to what he did. The only difference is he's put the premise that it depends on over here. I like to put them over there and have the number that we're. So this is the number line, just sentence 1, sentence 2, sentence 3, so that's how he's referencing them. He's filling out premise and tautology here. He'll stop doing that here in a sec.
Then what's these on the other?
And then these numbers are the premises it depends on. It's what I was doing right here.
He did it a little bit different. I like how he did it. Oh wait.
D or V,
I'm
not
talking about tautologically implies. You're saying 3 tautologically implies 4, or you're saying 5 tautologically, 3 and 4 tautologically imply 5.
3 and 4 tautologically imply 5.
So
So
that's
D
just-
is tautologically implied by 3 and 4.
And so
Yeah. It will always be and. One more note. Notice that this says conjunction. Conjunction here, when we say this, it doesn't necessarily mean only 2 things. It could be tautologically implied by one statement. If you want to think about the conjunction, you can just and it with itself. And you can take the conjunction of more than one statement as well. It's just saying, you just have to use, you can say, using this premise and this premise and this premise, as many ands as you want. Make sense?
this would make sense.
That does make sense.
Can we prove S without 4?
Now, S depended on all of these.
Oh yeah, that's right.
Because how'd you get D without 4?
Well, to say, could we have gotten this without this? Sometimes that's a hard question to answer because it just might be that you're not smart enough.
Right.
But one short proof way to do it is you just write out the whole truth table.
Right.
Yeah.
And if you did, you would have a cut. If there are multiple ways to.
Yeah, so you can write out this whole truth table, and you write the whole truth table without that premise, see if it's still a tautology. You write it out without premise, see if it's a tautology. Write it out without premise, see if it's a
Well,
tautology.
try out the whole truth table and then see which.
Well, remember this is what you're plugging in. You ultimately have to have a column, that's what you're saying. So yeah, you can have the whole truth table, but you're going to still have to have this column. And if you want to try getting rid of one of your premise, you're going to have the column that has all day except for that premise.
How fast would it take you to program a program for this? So you
Write a
plug in your
program for
variables, and then it give you the
He's
answer.
saying truth
Not
table.
long at all.
Not long.
No.
How long?
I mean, if you don't care if it has a crappy interface, like 10 minutes. So it's just logic. You can do logic real easy. I can do a loop that just spins while you give it inputs for variables that you want it to plug in true and false for, and then have it iterate over all the combinations and just evaluate it. Yeah, it's not hard.
That's why you become a programmer when you're going into logic. Test your.
Wow. I don't know about going into for logic because we're gonna get to a point where truth tables go out the window.
Right.
But if you're going into math, being a programmer was also really useful. So one of the things I do in my differential equations class is write programs for it. So in differential equations, a lot of times, there's a lot of problems that you solve that are somewhat similar in thinking to, you have a big formula and you have to plug in a bunch of numbers and do a bunch of math on it.
Right.
So there's things that are very similar that way, and you can find a grouping of problems that they're all kind of using that same similar formula over and over again. And so my professor let me do that. I would show him my program, and then show him how I got the answers for this problem, this problem, this problem, and just give him the answers, and he would accept that. He thought that was really cool that I did that.
That's genius.
How old was he?
Huh?
How old was he?
48.
Yeah, probably somewhere around there.
God,
Yeah, it wasn't, he might have been younger than that, actually. I don't think he was that old. Yeah, he's younger than your mom. Yeah, I don't know how old he is.
You know how old
But he was from
Mom is?
India.
58.
He's a fun guy.
Mom's not 58.
Yeah, she is. She's 10 years younger than that.
Oh, yeah.
Harold's not 40 still.
cow!
I I've always been telling people Carol's in her 40s.
Yeah, I tell people mom's 50.
You guys are terrible.
How old is Celeste?
12.
No, she's
Almost.
11.
She's
turning
11.
12 in
11.
September.
Turning 12 in September.
Mom's 40. Or 58. Seems old.
That is old.
I don't think
I'm
she's that
pretty
old.
sure.
She's not 58.
She's 10 years younger than
No.
She's like 51.
Mom is
Bro,
60.
she's 10 years younger than
Mom
that.
just turned 50
I
not that long
asked her.
ago.
My mom is 51.
In fact,
Correct.
Mom,
51.
Yeah.
Mom
Whatever.
is low 50s. Mom might be turning 51.
My mom is 51. And you
And Carol's younger than her.
or 50.
Yeah, she's not 58. That's too old.
That means she had last year when she was 47. But
Oh,
that
that's
was not
true.
true.
Yeah,
had last
she didn't
year
do that.
40.
She had her in her early 40s, if not 40.
She's not 51 though. She's past that.
I bet she's right. I bet she's either 50 or 50. Mom believe 49.
Stop it.
How old is Alan?
58, dude.
Ah.
Are you kidding me?
Okay, she
Anyways.
might not be 58, but I'm
She's
pretty
close to
sure when I
retirement.
asked her,
That's
she
the
said
first
she's
thing I
10
went
years
to
younger
that.
than dad.
Well, I can bet you good money that she's under 55. Happily do that.
We're gonna see.
Anyways, let's continue. So we did the proof. He just goes over some of the logical tautologies we used. So one of the tautologies was C implies not D. We kind of specified them as we went. C implies not D, and D tautologically implies not C. So he specifies some of the tautologies that we were using there. Ultimately says, yep, you'd have to do a truth table for that big old honking thing. A lot of reasons why that's a bad idea.
That is a lot.
Oh no, he's just going over the proof in more detail. Is this the same proof? Oh, so now he does the proof in a different order, only introducing premises when he needs them. And he's saying it doesn't matter if you would have done that first. So he's saying first list this is a premise, then this is a premise, then come to this conclusion. Then list this as a premise, then come to this conclusion, then list this as a premise,
That's kind of what you do
then
in
come to this
geometry.
conclusion. Yeah. It's more common that we do that in math proofs. We
Yeah.
plug in our premises as needed instead of plugging them all in to begin with
For sure.
and then referencing them.
Well, that's how.
But that's because the problem already contains them in them. In logic, it's common to just write your premises out so that you have them right there in front of you. You can see them as you're going to use them.
They already give you the premises, right?
Well, they give them to you in the sentence that you were reading. And you don't want to sit there and try and reason about the sentence to pick, okay, which premise am I going to use first? Typically, you want to write it out, symbolize real quick, so that you can make sense of it. And then you start thinking about how to use it.
Except Donnie, what if we didn't know that not B implies not A is the same as A implies B? So like, what if we didn't understand that? Then
Then you get stuck.
yeah,
And they think real hard. Welcome
It's
to
like,
logic.
What if you didn't understand that on a similar triangle, its base angles were congruent? Well, yeah, then you're stuck on the proof. Sorry.
okay. So when they give you problems though,
So we're going to have a set list of common tautologies that you would typically go to.
okay, that's what I was wondering. I was wondering if there's like some basic ones that they kind of give you so that you
Yeah,
understand.
so this was supposed to just be his first example. This wasn't, here's kid, try and figure this out real quick. Oh,
So
because,
these are actually going to start getting pretty complicated.
huh?
Well, that's
This,
the part
see,
that can't-
this kind of stuff, I'm telling you, some of the classes I crashed through, some of this was like the hardest stuff I saw. It was not really hard at all. I was very disappointed.
That'd be.
So we went over those two rules. Here he's making a point about an additional premise. So say I was trying to show that P or Q tautologically implies Q. He's saying, notice that rule number one, as we're doing this proof, so we were starting out with 1, we have P or Q as a premise, and that just depended on itself. And then you say, and now let's say we use rule 1, which says we can introduce a premise at any time. So now rule 2, we introduce not Q as a premise. There's 2.
See,
And
that's
then
why-
3, we come along and we say, therefore, oops,
Yeah, you did.
introduce not P. I don't know if I'm doing it the same thing now or different, but it doesn't matter. Same idea. So, not P, and now we come along and say, Q. And we say that's tautologically implied by 1 and 2. Well, now this depended on premise 1 and 2.
Just like,
So yes, it's valid to introduce premise however you want, but now what you proved is that Q is tautologically implied by premise 1 and 2.
right.
You did not show that it's just implied by this premise.
Right.
So while, yes, this proof right here is perfectly valid, it doesn't prove what we were trying to prove. So there's nothing invalid about here, right? If you take this as a premise and this as a premise, yeah, you can come to this as a conclusion,
But that's not what it gave you.
but we did not show that this is a conclusion which logically follows from just this.
So
So,
that's an inaccurate proof, is what you're saying?
well, I'm
Well-
saying that the logic here is perfectly valid, we just didn't prove what we were trying to prove. It's like I say, prove the sum of two evens is even, and you go off and you prove that there's an infinite number of prime numbers. It's like, yeah, your proof's great. If I asked you to do this, you did this. I asked you to prove that this implies this, you showed that this is implied by these two. You see?
Yeah.
So there's going to be times where we introduce premises, but then we get rid of them before it's over. It's how proof by contradiction works. We say, assume that we can add as a premise not this. That leads to something impossible, thus it has to be true to continue on our way.
You're right, she's 52.
52. Okay.
That makes sense.
That means mom's 50th birthday was a while ago. Advice. Alright. So that's what that conversation there is about. He's saying, yeah, you can introduce additional premise, just make sure that when it's all said and done, you prove that what you're trying to prove. Which in this case we didn't, because what we're trying to prove obviously can't be done. Okay. Now the next rule. The CP rule. CP for conditional proof. And you're very used to conditional proofs. These are proofs of the form. We kind of talked about this last time. Let's.
Life just wants you to bend over.
Yeah, it does. I need my leg to rest up. Okay. So let's say that we take as a premise. So premise, I'll even try to write it out kind of like how we've been doing it. 1, 3 plus 2 is equal to 5. Premise, okay? Now let's, or maybe we'll write it out in a sentence like the author did in that big ugly sentence. Given 3 plus 2 equals 5, comma, prove if x equals 2, then 3 plus x equals 5. Okay?
Right.
Now this is where we're going to introduce the idea of a conditional premise. We're going to conditionally let x equal 2,
And then pull that.
and then show that that means 3 plus x equals 5. So when it's all said and done, we're going to show, here's what we're not showing. We are not showing this. We're not showing 3 plus 2 equals 5, and x equals 2 implies 3 plus x equals 5. I mean, we will show that, but we'll reduce this to, that means that 3 plus 2 equals 5 implies x equals 2 implies 3 plus x equals 5. So we're trying to show that our premise implies our conclusion. You see what I'm saying?
Right.
Right.
So we're going to introduce x equaling 2 like this, but it turns out this and this give you the same thing.
Right. That makes sense. Because your premise is only 2.
Or
plus
when this is true. Should we do that real quick? Make sure I'm not lying. A, B, C.
Oh.
Ah, what a life. Alright, so So we can have
Oh man.
oh woman. Okay, so let's do this one first. So this one we'll call A and B implies C. You ready?
Yeah.
So true implies true is.
True.
True.
True implies false is.
False.
False implies anything is false.
No, it's true.
False implies, or sorry, thank you. False implies anything is true. 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 Wasn't as bad as you thought, was it? So there's only one false. Now let's do this one. So we're doing A implies B implies C. Right? So
Its antecedent is true.
true implies true is true.
And you don't need it anymore, right?
True implies false is false. True implies false is false. You see that one? That was kind of weird.
Right.
Stare at that one till it makes sense.
Yeah, it makes sense.
So we had true implies false here, which was false.
Right.
And then true implies false again is false. Good? Right.
False implies true is true.
False implies true is true. True implies true is true. False implies false is
True.
true implies false is,
True.
and then the antecedent's false in all these cases. So true, 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 true. And ta-da! They're the same. So let's make sure that we understand what we're doing. So what I'm saying is, when we're proving this, we add this as a premise to begin with,
Right.
so that we show that this and this implies this, and then we can remove it as a premise, so then we can say this implies this.
Which you what?
Because we're trying to prove an if-then statement. We're not trying to prove 3 plus x equals 5. We're trying to prove if x equals 2, then 3 plus x equals 5. Does that make sense?
Mm-hmm.
Okay, so that's what's going to happen with conditional proofs. We're going to add a premise conditionally, get our conclusion. So we're going to get something of the form like this, and then we're going to say therefore this.
Right.
Because this implies this, well, those are logically equivalent.
Right.
I'm going to say if this is true, then this is true, because it's told to you, but obviously because this, if and only if this. Make sense? So that's a bit of logic that we're going to use in these conditional proofs. Alright, so let's do one. Yeah, this uses one. So notice that therefore is an if-then statement.
National League race.
Okay. Did we ever say the CP rule exactly? Let's read the rule exactly and then continue. I think I just went into an example first. So rule, conditional premise is what the CP is. If we can derive S from R and a set of premises, so if we can derive S from R and a set of premises, in this case we only use one premise, but I could have had add and a whole bunch of premises, right?
Oh. Okay. There we go. Yeah.
So if we can derive S from R and a set of premises,
That's a B. Your
What?
second one. S from R.
alright. So if we can derive S from R and a set of premises, so if S and R, if R and our premises imply S, then we can derive R implies S from our premises. So if our premises and R implies S, then our premises implies R implies S. Make sense?
That's cool.
It's basically this truth table right here that we're
show
using.
that's the case.
Except for to prove it, we'd have to have like this A, B. Well, no, it doesn't matter.
That's not what that's saying.
It is what that's saying.
Your premises aren't implying S.
If we can
Alright.
derive
Right?
S
Implying R implies S.
from R and a set of premises.
Uh-huh,
So you have all your premises and R.
right.
If that together implies S, then your set of premises implies R implies S. So if you can derive S from R and your premises,
Oh,
then you can derive R implies S from your premises,
okay.
which is exactly what we showed right there.
Yeah.
Does that make sense?
Yeah.
All right, let's do this proof. Whew. Okay. All right. So if the cards are third, then if the Dodgers are second, the Braves will be fourth. So we have 1. Cards implies Dodgers implies Braves.
Just have just a small number.
Make sense?
Mm-hmm.
Next sentence. Either the Giants will not be first or the Cards will not be third. So
Cards will be
either,
third.
or the Cards will be. So either Dodgers will not be first. Before we were saying the
The
Dodgers.
Giants will not be first.
Jeez, I keep mixing up. The Giants. We haven't said anything about the Giants before, right?
Yeah.
So either not Giants or Cards. Did I get that right?
Yeah.
So we have not Giants or Cards, like that.
Be third. Oh, that doesn't.
Do you think the numbers even matter?
They shouldn't. If they do, then we can do like C sub 1 or whatever. But I doubt we could because of how small it is.
The Dodgers will be second.
In fact, the Dodgers will be second. So 3. We've
It's
got
like
to
he's
be.
having a conversation and he's skipping the other person's input. Or like he's has a question and then he's researching it.
Yeah.
Alright, therefore, if the Giants are first, then the Braves will be fourth. So we're trying to show Giants implies Braves, right? That's what we're trying to prove.
Yeah.
Okay. Let me pick that up here. We're trying to show Giants implies Braves.
And the only way to do that is to show Giants is true and Braves is true, right?
No, we're trying to show that if Giants is true, then Braves is true.
I know, and the only way to show that is through our 1, 2, 3, 4, 5, 6.
So we're going to introduce as a premise 4. We're going to introduce Giants as a premise
Right.
Which means not C.
as 4.
Oh,
Huh?
we.
That's like introducing x equals 2 as a premise over here.
Yeah.
So we let x equal 2. We show that implies this. Then when it's all said and done, we're going to get rid of that premise and replace it with it shows this.
Right.
So now I'm just trying to show that B is true from what I have here, right? You with me
Yeah.
on what we're trying to do?
Yeah.
Okay, so I know G and I know not G or C.
Why do you know?
So you know
So you know not
not
C.
C.
No.
So I know C.
Yeah, because it's not
Look.
and.
Let me say something neither way.
Oh,
G's false or C's true.
Right.
Well, G's true.
Well, C could still be false.
G's false or C's true.
Let's see. I don't show you the markers. I say I'm not holding a blue or I'm holding a black. Okay?
Okay, now we know you're
I'm not holding a blue or I'm holding a black. I show you I'm holding a blue.
You're not holding a black.
I have to be.
Alright, okay, yeah. You're right, you have to be.
I'm not holding a blue or I'm holding a black.
Right,
Well, I am holding a blue.
right. So you have
G
to
is
hold-
true. This is false. If false or something is true, then the other thing has to be true.
Right. Right.
So we know C is true.
So 2 and 4 tautologically imply what?
C is true.
C. Exactly. So I know that C is true. That is tautologically implied
How did we do the last one then?
by 2
We're talking about 3.
and 4.
I'm so.
How did we find G is true?
How did we do the last proof?
We
then?
just introduced it.
We were using implies.
We're always using implied. We're using tautologically
we were
implied.
using
Oh, we used
and.
or.
No, we were using and.
I don't know. Look,
Oh wait, never mind.
No, we weren't. We were using or.
if you're that curious, you can go back and watch it when we get there. Just make sure that this makes sense.
Okay.
Either G's false or C's true. I know G's not false.
We were using implies.
Yeah, we were.
We're using,
So C's true.
We're using not G implies C.
Are you good on this?
No.
Okay, so we just introduced
We
G.
literally did the same thing
Just
last
cause?
time.
No, we didn't.
Yeah. we
Forget
did.
what we did last time. Does this make sense?
No, it doesn't, because it doesn't make sense with what we did last time.
Okay, listen to his logic though.
Does this make sense? Oops.
When can or
Does it make sense that that is a tautology? In fact, we just barely did this tautology right here. M or P and not M implies P. M or P and not M implies P.
Okay.
Make sense?
Yep.
Okay.
Yeah, there are 1,000 ways to show these things.
Okay, and this depended on 2 and 4. Right?
Yeah.
These are the premises depended on. Okay, 6. So now that we know C, what do we know? We know that D implies B.
Right.
Right? And that's tautologically implied by 1 and 5. And we've now used premises 1, 2, and 4. Any questions there?
How are we gonna get rid of 4?
I gotta get my brain in the game.
When we go from this to this,
Okay.
How did we use the premise 4 in that?
because we use line 5, which is premise 4.
Yeah.
Oh, okay.
This depends on premise 4, and if this is using this, it still depends on premise 4. Make sense?
Yeah.
Okay, so now we got D implies B. Now, from D implies B and D, we get it's the big old B number I'm going to write here.
G implies.
B. We now know B. It's tautologically implied by
Oh,
6
yeah.
and by 3. And we've now used premises 1, 2, 3, 4. And that's what we were trying to get to. We were trying to show if G is true, then B is true.
No, we need it. We're trying to not use 1 though, I thought.
No, we're trying not to use
No,
4.
now we do 8. So now we know that G implies B. And that is tautologically implied by, I don't know how to say that. How does he say it?
He said tautologically implied.
Oh, 4 and 7. Oh, duh, different rule. Because now we're using conditional probability. So this we can see from CP. We're using conditional probability on 4 and 7. And so now we're only using premises 1, 2, and 3. So let's make sure we understand this.
You're using 4.
Hold on. Line 4 is where I introduce G as a premise.
Yes.
That's equivalent to let x equal 2.
Yes.
G. Therefore,
B.
3 plus x equals 5, B. Therefore, 3 plus 2 equals 5 implies if G, then B. And we're no longer relying on x equals 2, or we're no longer relying on g being true. We're just saying if g is true, then b is true, is what we proved.
Right.
You good with that? So one convention I noticed some people use that I kind of like is when they're doing a conditional proof.
Oh, they gave you the conditional proof right there. Therefore, if giants are first. That's why we
Right.
put
This
it
is what I was trying to prove overall. G implies B.
Yeah, that makes a lot more sense.
So I introduce G, show that then B is true.
Right.
Therefore, G implies B is true. Right? So what I notice some people do is when they're doing a conditional proof, when they introduce the extra condition, they indent until they're done with that condition, then they go out and continue with the proof. Because notice, if this proof continued on for some reason, I can no longer use G's true anymore.
Right.
So if you were doing some algebra proof, and for some reason inside the proof you need to use the fact that if x is 2, then 3 plus x equals 5, you might, while you're doing a proof, do a quick side proof of that, and then continue with your proof, and as you continue, you no longer get to use the fact that x is 2 anymore.
Right.
That was just to show that this thing right here is true, because you need that later for something. So similar thing with these. In this case, we didn't really need it, but just to help you keep your thinking straight, when you start conditional proof, they indent until the conditional proof is over, then they come back out. Similar thing with proof by contradiction. When you introduce your contradicting premise, continue with it indented until you reach your contradiction, and then continue. Sorry, we haven't talked about proof by contradiction yet. Whew. What time is it?
9:46.
Holy cow. 9:46?
I don't know.
Is that just your connection?
That's my, yeah,
Ah,
9:42.
jeez. Okay. Well, we can continue from there, I guess. So where are we ending? We're ending basically in the middle of 2, 2.
So, look, you don't think it is the
So
end
what
of
should we do
2-2?
for?
No, we haven't even gotten to proof by contradiction yet, but that's basically the last thing. So we're just going to go over more examples, helping you get comfortable with these rules. And then the next section, 2.2 is getting you comfortable with these rules. Section 1 was the hardest one. This one's the next hardest. Section 3, he's just introducing you to a bunch of tautologies and
That's what I'm
ultimately gives
saying.
you...
Are we at the end of section 2-2?
We should be close to. Because section 3, now I'm in 3, and he's just going over a bunch of different tautologies, and it gives you this table saying, here, all these are tautologies.
Wow.
So these are the common ones that you'll use, and there's the names of them to the left. And then the last section is where he introduces proof by contradiction, or indirect proof is another name for it. And then we're done with chapter 2. So we'll continue from there next time. I'll try to get these uploaded if you're going to continue to do this, so that you can go back and watch the first lecture.